Good morning, everyone. I'm glad to see that you guys at least made it to the second talk of this day. I mean, that you're not still in bed. Before I start my talk, I quickly sort of want to like you guys to raise your hand. Who has ever heard of Kubernetes before? Oh, whoa. Okay, that's a lot more than expected. Then I can just skip 10 slides. No, just kidding. So who of you has heard of FreeBSD? Well, of course, everybody. Who of you has heard of CloudABI? Okay, well, still half of the hands raised. That's pretty impressive. So, okay. I'll speak even closer. Should not swallow it. So, yeah, my name is Ed Schouten. I've been a FreeBSD developer since 2008. Initially, I used to work on terminal, TTY stuff. People nowadays still send me bug reports and hope that I fix stuff there, but I'm too busy nowadays. Sorry about that, guys. Nowadays, I'm more focusing on security, cluster computing, etc., which is why I'm giving today's talk. So this, like, the title of the talk is also going to be sort of my outline for today. I didn't have a separate outline slide. First, I'm going to talk about Kubernetes, what it is, give like a short introduction. Then I'm going to talk how Kubernetes is related to FreeBSD or how we could get it running on FreeBSD. And then later on, I'm going to talk about CloudABI and how I'm throwing all of these three different components in the mix and why we should be doing it in the first place. So let's first start off with Kubernetes. So Kubernetes is a cluster management system that has originally been developed by Google and is sort of inspired by their sort of proprietary cluster management system called Borg that I also used a lot in the past while I was working for them in Munich. The main difference between Borg and Kubernetes is that Kubernetes is written in Go, and this was sort of, whereas Borg is written in C++, and this is sort of done on purpose because there were like a lot of design flaws, things that could have been improved on Borg. So what they did is they picked a different language, so they were sort of required to rewrite all of it and sort of cherry pick all of the things that were good and leave out all of the things that were bad. So what happened is that Google like wrote this initially, released it as open source, put it on GitHub, and then later on donated it to something called the Cloud Native Computing Foundation. And the Cloud Native Computing Foundation is sort of a branch of the Linux Foundation where sort of all projects end up that are related to cloud computing, cluster computing. So other projects that are part of the Cloud Native Computing Foundation are Prometheus, a monitoring system, which I think is pretty awesome and also used on a like day-to-day basis. And another pretty popular one is gRPC. So that's Google's RPC framework that is built on top of protobuf, which is also sort of a re-implementation of a proprietary system they had internally called Stubby. But Stubby was too hard to open source because it also sort of tied in with a lot of other Google infrastructure too tightly. So that's why they sort of made a clean slate approach and donated it to the CNCF. So like almost I think all of the projects that are part of the CNCF, it's Apache 2 licensed. So that's pretty favorable for us, of course. I mean, it's not the BSD license, but still better than the GPL, in my opinion. So to sort of give like an explanation of like the model behind a Kubernetes cluster, you have to sort of get used to the terminology that Kubernetes uses to sort of understand it properly, how it works. So one of the common phrases you often hear when people are talking about Kubernetes is nodes, and nodes are just Linux servers, just your average Linux installation. It doesn't matter whether it's a virtual server, a physical server, whether it's running on AWS or on Google's own cloud computing platform or on your own hardware in your basement. It doesn't matter. It's as long as it's running a Linux kernel, it's a node. So on top of those nodes, you want to be able to run containers, Docker containers in the case of Kubernetes. And a container, in my opinion, can be defined as like a group of Unix processes that share the same process/file system namespace. So processes running in a container can all like send signals to each other. They can store files somewhere in the file system that become visible to other processes running in the same container, etc. Kubernetes has sort of added like one layer on top of containers called pods, and pods are groups of containers that need to be scheduled together on one node. So they're like the smallest thing that can be scheduled on a cluster. So it's impossible to start just a single container on a cluster. You always have to create a pod that is running one or more containers, not 0 containers. That's pretty much useless. So every pod has its own RFC 1918 IPv4 address, so 10.0 point something. You can just configure which range needs to be used. And all of the processes that are running in like the containers in that pod all have to make use of that single IP address. So you can't have 2 containers that both listen on port 80. They must be listening on a different port. Then you often, like when you do cluster computing, you want to start a whole bunch of pods that are, well, pretty much identical to each other. So, for example, you've got a web application that you want to spin up 10, 20 times, maybe 100 times, maybe 10,000 times. It all needs to be sort of the same template of a pod that you want to start. And this is what Kubernetes calls a deployment. So a deployment is sort of just literally a template for what a pod should look like. And then you're just saying to Kubernetes, I want to start like 100,000 of those, and it will, well, if you only have a small number of servers, it won't be able to schedule it, but if you pick a sane number, then it will spin it up properly. So all of these objects are configured through JSON or YAML files. It doesn't really matter. You can write JSON, you can write YAML. Kubernetes accepts both. YAML is a bit more easy to read because the files tend to be rather big, and then just having like JSON all smashed onto one line, that's pretty much unreadable. So, oh wait, no, it's not going to that. Why is it? It's scrolling instead of going to the next slide properly. Yes, so here's a picture of what a simple cluster might look like. So this is a cluster consisting of 3 different nodes, and these 3 different nodes are in total running 4 pods, and these were instantiated by 2 different deployments. One of them was called DB, simple deployment that spawns like maybe a MySQL container that just serves incoming requests, handles SQL queries, and maybe you have some kind of maybe background scrubbing FSCK-like job that, I don't know, MySQL doesn't need this, but if you would have maybe a sort of somewhat more complex database system, you might have some kind of background scrubbing job that scrapes over the data set and prunes that data, for example. And then there's a second deployment at the top that is sort of being spread out across multiple nodes in the cluster. And this deployment was called www and contained one container engine called Nginx. And what happens if you spawn this up, then it creates multiple pods, but because all pods have to have a unique name, it adds some garbage at the end. So you see that one pod was called www-a30d, etc., some kind of random hash. It just needs to add something to make it unique. So that's where all that random garbage comes from if you take a look at a Kubernetes cluster at the pods that are running. So on all of the nodes in the cluster, you have a process running called a kubelet. And a kubelet is basically a tool that looks at like the stuff stored in the API server. So the API server is sort of like a database that keeps track of everything that needs to be running, and sort of compares against what's running on the system itself. And if there's any discrepancies, it just spins up more containers and reports back status on whether that's successful or not. So by default, the Kube API server doesn't have any event loops in it. It's just a sort of static server, and the only thing it can do is it can keep track of what needs to be running on the cluster. So in order to spawn up jobs properly, you need to run 2 other jobs somewhere. They can even be run on the cluster somehow, but you can also run on a separate server. Doesn't really matter. And one of them is called the Kube scheduler, and it takes a look at all of the pods that are sort of registered in the API server, and looks at the ones that are not being scheduled on the node right now, and then picks a node. Like it has some kind of bin packing algorithm or some kind of algorithm in place to determine what's like the best place to run a certain node. And then there's another node called the Kube controller manager, and that one is sort of also responsible for like all the miscellaneous event loops, actions that need to be run on nodes in the cluster. So for example, this is the job that hands out IP addresses on the cluster. So this job basically says it gets a list from the API server of all the nodes and says, this specific node in the cluster needs to make use of this IPv4 range. So here's a simple example of how you would spawn a simple pod on the cluster. So not using a deployment, but just a single set of containers that needs to be scheduled on some node. You just write a YAML file where you say this YAML file declares a pod. It doesn't declare a deployment, but just a pod. And this pod should consist of these containers over here. In this case, just a simple Nginx container. So in this case, for the image, you can specify a very simple name. If you just specify a plain name like this, it will go to Docker Hub and just download the image under that name. You can also specify a full URL, and then it points to your own on-premise container registry service. So another sort of important aspect of Kubernetes is how they do networking. This is again done using like some separate tools, some separate concepts. One of them is called services, and a service is basically an object you also register in Kubernetes, and it's sort of a matching on pods that sort of says like these pods, they together form some kind of like uniform service that needs to receive load balanced traffic. And if you create a service, it adds like an additional IPv4 address to the cluster, and if you communicate over that IPv4 address, you don't end up on a single pod, but you end up being load balanced across all of the pods that are part of that service. To make all of that work, there are two separate daemons that you also need to run on your system. One of them is called kubeproxy. And kubeproxy is not really a proxy, but it's a tool that basically scrapes the state from the API server on which services are being registered and generates like a whole bunch of IP tables rules to do load balancing across the nodes. So yeah, this is just a job that runs in the background on your server. You can you could run it through Kubernetes as well through some hacks, or you could just set it up with an init script on the node itself to run on startup. Then there's another service called kubeDNS, and what that thing does is it allows you to resolve services by name. So in the case of that web server, if I would create a service called www, then kubeDNS allows you to resolve the hostname www.namespace.cluster.local or with some kind of suffix to the RFC 1918 address. You have a question? Yeah. Oh, so the question is there a reason why it's an RFC 19 address? Yeah, so you need to use an RFC 1918 address here because the entire idea behind Kubernetes is that you want the cluster to be like internal. You shouldn't be like literally exposing a cluster with all of its internal addresses to the public internet directly. Why it's using IPv4, it's mainly because the Google developers are too lazy to add IPv6 support. That's the main reason. There is a ticket open on GitHub for adding IPv6 support, and it's been open for a couple of years. So they're still using IPv4. Yeah, it's like, why are bananas curved? There's little we can do about it, right? Then this is only about like how sort of cluster internal network traffic works. A very important thing is how do you get external traffic coming to the cluster? Well, they have some separate concept for that, which I'm not going to discuss today, called ingress controllers. And this allows you to spawn jobs that take traffic from public IPv4, IPv6 addresses and route it into the cluster over the internal IPv4 addresses. So what are the weaknesses of Kubernetes? I'm first going to start off with that. So the networking, IPv4, mentioned it before. It's a shame that it's not using IPv6. Also the fact that it's allocating a single /24 for every node to like schedule for addresses to attach to pods. You may actually run out of addresses quite quickly. I mean, say if you own a cluster with 256 nodes, you're already using up a /16 just for running some pods, which is quite aggressive. Another problem you have is because there's quite a sort of they make use of NAT, proxying, all that kind of stuff to make load balancing work. It's actually pretty hard to trace traffic properly. So some kind of front-end job, a web service doing that like a SQL, sending a SQL statement over to a database backend, but it's not working properly. How do you know which server the traffic was sent to? You only see traffic going from the pod's IP address to a service address of the database system. And how do you know which database backend was being used? Well, you see that a lot of people add all sorts of hacks. You know, for example, if your backend is a web service, you add some kind of HTTP response header to know which backend you're making use of, which is a bit sloppy in my opinion. Something we've noticed at Kumina, where we're making use of Kubernetes in combination with Docker on Linux, is kubeproxy can actually get stale, and then you sometimes see traffic being misrouted to like random other backends in the cluster. You know, addresses are being reused quite aggressively in the cluster. So this one time we actually had a problem where we were like restarting some jobs on the cluster, and then we saw user traffic actually ending up on the staging setup, even on the wrong job. It's just because they're reusing addresses so aggressively, traffic can go to the wrong jobs. Initially, Kubernetes didn't have any support for network policy, so all of the containers running on the cluster could basically chat with each other. So security was pretty bad. They later on solved this by adding network policy support, but that can only limit incoming traffic. So you can't specify which traffic a container can generate. You can only specify which traffic a container can receive, which is somewhat of an improvement, but still not ideal. So if you're using sort of Kubernetes to run a multi-tenant cluster, I would strongly advise against doing that. It's not pretty wise. Also, on like the computing side, so just ignoring the networking for a minute, containers, they don't really take the complexity away. So every container is a full Unix environment, having all of its 1980s Unix features in it. And what I've noticed is we sometimes get like junior systems administrators, and we can like really easily explain to them how Kubernetes works. You know, you just run a single command and you can spawn a dozen jobs, but then you sort of have to help them debug Unix issues, explaining them why standard out on the container needs to, or on the job running in the container needs to be made unbuffered, otherwise messages don't end up in logs, all of that kind of nonsense, that sort of remains and is sort of slightly annoying. Also, the attack surface with the kernel is quite huge. You know, Linux is an operating system that supports, 300, 400 system calls, and all of those need to be container aware. You have special file systems like /proc being mounted in containers, and you know, Linux proc is polluted with a lot of random files. You need to sort of be certain that there's nothing in there that should remain hidden. So again, for running completely untrusted jobs, you know, for building a cloud computing service and using Kubernetes in the backend, I actually wouldn't, you know, think it's secure enough to operate a single cluster where you're running jobs for multiple customers. And also, like the final thing that I think is quite a weakness of Kubernetes or containers in general is that it actually creates this sort of cargo cult programming culture where a lot of the containers need to copy paste a lot of garbage over to make it work. You know, Docker files that are 100 lines long, shell scripts that are only useful for starting up a binary in the end that are also 100 lines long, combined with Docker images that are hundreds of megabytes in size, containing a whole set of like glibc core utils, only to run a very simple web application. I mean, that's just copy-paste programming. Wastes a lot of disk space, adds a lot of security issues, of course. It should be a lot simpler. People should just write a small web application, just write some code, and then just press a play button and run it on their cluster. They shouldn't be thinking about, you know, just running entire Linux distros inside of containers. Still, there are some things that are pretty good about Kubernetes. It all works quite reliable. The automatic rescheduling works pretty well. We use it at Kumina, and we don't get paged in the middle of the night that often anymore. You know, whenever a system crashes, you know, some disk breaks down or something goes wrong with the networking interface on some node, it just gets disconnected from the rest of the cluster, and Kubernetes just spawns a job on some other node in the cluster, and everything's all right. kubectl, the tool is really friendly to use. You know, if you've used it for a day or so, then you basically understand 90% of its functionality, which is pretty good. Docker Hub is also pretty good in the sense that you have packages for anything you can think of. You have Docker images for anything you can think of. And the project, so the Kubernetes project, has like a lot of funding and momentum behind it. It isn't going to disappear anytime soon. So FreeBSD. Oh. Yeah, so the question is there any way to properly trace what's going on, to figure out what's going on when a container has failed? Yes, so what's pretty cool is that containers aren't, like, the state of a container isn't being thrown away immediately. You can always run kubectl describe to describe a container that is already terminated. And then you just get sort of a couple of screens of text giving all sorts of metadata about the container, when it was started, when it was terminated, why it was terminated, and also some log entries related to that. So those are not log entries generated by the program, but log entries generated by Kubernetes in the process of starting and tearing down that specific container. In addition to that, there's also a logging facility in Kubernetes, so you can run kubectl logs and then the name of a pod, and then you can actually take a look at the pod standard out, standard error. And it also has flags like -f and -- timestamps to prefix timestamps to the output and also follow the output while it's being generated. So at first, when you start using it, you might have the feeling that you're sort of losing control and that things might becoming non-transparent, but in practice, I haven't really run into those issues a lot. I mean, you get used to it after some time. Instead of browsing through var log, you now have to use kubectl, and that's all pretty well. It's perfectly manageable. Did that answer your question? Okay. So now the first question we should be asking ourselves, could we port Kubernetes to FreeBSD? Well, we likely could. I mean, some people are already working on getting Docker working on FreeBSD, and I heard from some people that it's a hack job, but some other people will probably step up to clean it up, and then it might work after some time. We could also make compat Linux in the kernel more complete to be more Linux-like, so jobs running in a container have less of an idea that they're running on like some broken version of Linux, but actually think that they're running on a real version of Linux. We could maybe even adopt some more Linux-specific frameworks like C groups to make resource limiting and network policies like make it work. Now, well, we could also maybe extend Kubernetes to support PF instead of IPE tables to do the networking. So there's like a whole bunch of options, a whole lot of things we can do to make Kubernetes work on FreeBSD. But, next slide, should we port Kubernetes to FreeBSD? Well, consider this discussion. Somebody like from the Linux world says like, why bother? I'm going to start up Linux-based containers anyway. Well, then your answer would be, yes, but at least our cluster is based on FreeBSD, which is awesome. It's BSD tech, BSD license, yada, yada, yada. Then the other person says, like, what's the advantage of that? And then you say, well, in practice, not much. And then, are there any disadvantages? Well, yeah, the jobs crash every couple of hours, and, you know, this doesn't work. And, you know, this Node.js container or something popular, no, it doesn't work. No, you can't run Rust programs because we haven't implemented that yet. So we could go in that direction, but I think the end result is this will only make BSD look bad and also, like, uncreative. We're only trying to follow, catch up with Linux instead of doing something awesome. So what I think we should do instead, simply accept that people want to use Linux servers to run Linux containers. Don't even try to compete with it. So go out of, don't get into these arguments, that don't make any sense, where it's just us trying to catch up with BSD. It's a cat and mouse game, and we'll always lose that. Instead, we should see if we could at least integrate with Kubernetes in a certain way. And with that, I mean trying to see if there is a place for FreeBSD nodes inside of a Kubernetes cluster. See if we could come up with like Kubernetes nodes that actually provide some additional value over simple plain Docker containers. Focus on niche markets instead of focusing on like the 90% of users. Focus on like the 10% of companies that actually do software development in-house instead of firing up plain Apache and Nginx containers, and actually try to appease those kinds of people. So in the process, we should try to tackle the weaknesses that Kubernetes on Linux has, and with that I mean try to improve security and try to make things more minimal. Development headcount on FreeBSD will always remain less than Linux, or at least for the foreseeable future. So we should try to keep things simple and, not add a lot of garbage that the people in the end don't use. Just, KISS. That's basically what I want. So now I'm going to talk about CloudABI and, later on discuss where I think the CloudABI fits in this picture. So this is sort of like a recap of my CloudABI talks that I've given in the past. So CloudABI is sort of a heavily stripped POSIX-like programming environment. And the entire goal behind it is to sort of make programs behave like black boxes. So programs can't just open arbitrary paths on disk. They can't create arbitrary network connections to the outside world. They're really just black boxes that need to be plugged in before they can be started. That's sort of the entire goal behind it. So these dependencies on the outside world are expressed as file descriptors. So for example, if you want to make a program communicate with the network, then you must make sure that you start it up with a socket injected into it. If you want this program to access parts of the file system, then you need to inject file descriptors of directories into it to make it work. So all in all, you could think of it as a sort of capsicum-like programming environment. The only difference is that capsicum is essentially always turned on. Well, this model has a couple of advantages. So first of all, one thing that's not on the slide, but what's pretty awesome is that it makes it easier to port software over. Because all of the features that are incompatible with capsicum have been stripped out, you can just compile your software against CloudABI, 90% chance it won't build, but then you at least have sort of an inventory of all the things that need to be patched up to make it work properly. Whereas with capsicum, everything just builds out of the box, but as soon as you start it, it doesn't work because you know, the sandboxing that you're trying to apply to it is far too strong. So these programs can be like really tightly sandboxed. They can also easily be tested because the nice thing is they don't try to sort of open arbitrary paths on disk. You really have to sort of feed them files and directories that they can use. So if you want to instantiate CloudABI programs multiple times, well, it's pretty easy. Just inject different kinds of resources and you can be quite certain that those programs won't conflict in any way. And also because all of the dependencies are sort of known up front, you can deploy them a lot easier because you know, you sort of have an inventory of what kind of things they use. So on the next slide, there's an example, a simple C++ web server that is built on top of CloudABI. Some of the includes have been left away and some of the details missing, but it just consists of two parts. So first of all, instead of trying to open like network sockets and directories directly, it gets it out of a structure called the arc data. So the entry point no longer has string command line arguments. It sort of has a YAML-like tree of attributes that can be passed into the program. And the neat thing is that file descriptors can be attached to this tree. So it's not just like plain scalars, strings, ints, etc. It's also that file descriptors can be added as attributes pushed into the program. So this program loops over all of the attributes that are received and extracts a HTTP socket and a root directory. So once all of that stuff is finished, it can go to a second loop where it starts to process incoming network connections using accept. Here could be some code to parse HTTP GET requests. And in the end, maybe some file needs to be served back to the user, so it uses OpenAT to open a specific file on disk. So in this slide sort of explains how these programs can be started up. First of all, we need to run them through a separate cross-compiler that you can install from FreeBSD ports. And once we have it compiled, we need to load a certain kernel module called CloudABI 64. And this adds support for running 64-bit CloudABI processes. So, of course, there's also a kernel module called CloudABI 32 that allows you to run the 32-bit processes. This configuration then explains how the program needs to be started up. This is just some YAML way of referring to a certain namespace, a certain tag namespace as it's called, but this is like the most interesting part. What we're saying here is HTTP socket needs to be a socket that's bound to port 80, and this will sort of be replaced by a file descriptor. And also for the root directory needs to be like replaced by a file descriptor, and this is sort of all passed into to the program when we're running CloudABI run and passing in the YAML file. So is this clear to people here sitting in the audience? So what are the changes in CloudABI since 2015? The ABI is now formally specified. We have like a CloudABI.txt, 2,000 lines long, describing all of the system calls and data types, and this allows people to reuse CloudABI on different operating systems. So we automatically generate C header files from it. We could even generate bindings for different programming languages, so for example, Rust, etc. Support for more hardware architectures. When I first announced CloudABI, it only worked on x86, 64. Nowadays, it runs on 4 architectures. FreeBSD 11 has been released in the meantime, so support for CloudABI is sort of integrated into it. Just install FreeBSD 11.0 or 0.1, and then you have some proper support for running CloudABI software. Also pretty awesome, we can also emulate it in user space nowadays. So even if your operating system doesn't provide native support, you can at least run like an unsecure version of CloudABI in user space, at least test around with it. And also more software has been ported in the meantime. So if you want to know more details about this, FreeBSD journal from May 2017 has a pretty good article on it, what has sort of changed over time. So now, sort of with the introduction ahead, now we're actually going to look at the interesting part, like the huge long build-up for all of this. So now we're going to take Kubernetes and replace Linux with FreeBSD and Docker with CloudABI. How did I do it? So when we at Kubernetes started using Kubernetes, we were still making use of Kubernetes 1.3, pretty long time ago. And back then, Kubernetes was still pretty simple. If you sort of looked at how the kubelet daemon was implemented, what it did is for every pod that needed to be created, it invoked Linux system calls to create C groups, set up the networking, etc. And then when it wanted to create containers, it would call into the Docker daemon. And the Docker daemon would then download the Docker image you would specify in the pod YAML file. And once downloaded, it would spawn containers inside of the pods that Kubernetes set up. So there were actually two things sort of wrong or annoying about this model. So first of all, it's sort of strongly tied against C groups. You know, this contained all sorts of Linux-specific code to create C groups to set up the networking, and the Kubernetes people weren't happy with that. Also, it's strongly dependent on the Docker daemon. Within the Kubernetes community, there was also some discussion about using different container formats, so Rocket, OCI containers, etc. So what they did is in Kubernetes 1.5, they introduced an API called the Container Runtime Interface, CRI for short. And what happened is that they just split it up in multiple daemons. So kubelet now doesn't have any understanding about container formats anymore. It also has no understanding about C groups anymore. It's just a random Go app that connects to the API server, takes a look at what it needs to be doing, and then forwards those requests to RPCs. And it now makes use of two separate daemons. One of them is called the image service. And with the image service, it can, the kubelet sends over RPCs to download Docker images and maybe even remove them. So it also takes a look at the free disk space on the node, and if that's getting too low, it might send RPCs over to the image server to throw away certain large container images that haven't been used for a long time. And there's the runtime service. And the runtime service implements sort of the old logic of creating those C groups, and it sends RPCs over to Rocket, OCI, or Docker, etc., to spawn the containers inside. So what I decided is to make use of this container runtime interface feature to add support for CloudABI. So what I've written a couple of daemons collectively called Scuba. Scuba means secure Kubernetes, Scuba. And it consists of like two separate processes, namely a runtime and an image service written in as CloudABI processes. So these jobs already run as CloudABI processes on a FreeBSD box. And the image service is quite simple. Instead of downloading like a fully fledged Docker image, the goal behind the image service is to download an ELF file, a CloudABI executable, and store it in some kind of directory on disk. Then there's the runtime service, and what it does is, the only thing it does basically is just fork and run those ELF files that are being provided. I've added an extension to Kubernetes that instead of using command line arguments, environment variables, that kind of stuff, the arc data YAML specification can actually be placed inside of the Kubernetes pod specification. So normally when starting a CloudABI application, you would make use of tags like socket and file to access the disk and networking. Well, these tags are gone when you're using Scuba. Instead, you just get some tags that are really specific to Kubernetes, to the environment at hand. So, for example, there's a tag called Kubernetes/container log. And if you place this one in the YAML file, the process basically gets a pipe in which it can write, and everything that's written in there ends up in a container log. For networking, I've also added various tags like Kubernetes/server and Kubernetes/client, where you can say, this is a program that needs to be started with a networked service. So this will add sort of this will hand over sockets to the program on which they can do networking. Then there's another tag called Kubernetes/mount, and if you use that one, you can refer to disks or to paths on the system. So for example, Kubernetes has built-in support for doing NFS mounts or attaching Amazon EBS volumes. All of that kind of stuff is supported, and you can attach those directories, those mount points over, you can hand them over to the CloudABI process using Kubernetes/mount. So this is sort of like a picture of what my setup looks like. So instead of using Docker, it's just a kubelet talking to Scuba image service and Scuba runtime service. So Scuba image service downloads an image from the internet, places it in a certain directory on disk, and then the Scuba runtime service gets the ELF from this location and spawns the jobs over there. Yeah, so I got this working initially. I got some very simple jobs to run. I could run a very simple HTTP server. I could run a sleep executable that would just stay in a loop, write some entries into the log file and nothing more. I started to realize after some time that the way that like CloudABI did its networking, or well, Kubernetes does its networking for what it's worth, is sort of fairly suboptimal. And this basically boils back to some of the slides I gave earlier during my talk that like IPv4 is easy to exhaust, etc. So the problem with APIs like bind and connect, so the traditional API for binding to a certain port number or connecting to some other host on the network, is that they require a lot of security frameworks to be secure. You need IP tables or PF to actually generate, hundreds of lines or maybe thousands of lines on an average node to sort of come up with a secure policy. Another problem with these functions is that they also require extra kernel frameworks to do tracing and debugging. The fact that I always had to log in on Linux servers running Docker containers, in a Kubernetes cluster to run TCP dump, that's all fairly annoying because you get so much garbage in there. There's no easy way where you can just say, like, I want to capture only this traffic for this specific pod or container, just using a pod or container's name. There's also no support for metadata passing. So all of these APIs are IPv4 address-based. Whenever a container receives an incoming connection from some other pod on the cluster, it only gets an IPv4 address. And it needs to somehow do a reverse lookup to actually figure out which container tried to contact it. So what I've done is I've written a daemon called Flower, which I jokingly sometimes call Sockets as a Service, SaaS. Sometimes also call it like a dating service for Unix apps. And it's nothing more than a daemon where you can send RPCs to register yourself as a service. And you can send other RPCs to just connect to those services that are being registered. So what Flower does whenever there's sort of like a match, you've got one server running and one client trying to connect to it, it creates a Unix socket pair and then hands out the file descriptor to both ends. So it uses file descriptor passing. And this project is sort of unrelated to Kubernetes and CloudABI. I mean, in practice, you'd likely want to use those two in combination, but in theory, you could use it separately. So how does it work? First of all, you start a process called the switchboard, and it's just like a traditional patch panel. And what you can then do is you can run these other commands, flowercat, which is a bit like netcat, to like listen on the switchboard and connect to a process listening on the switchboard. And you can use these labels to sort of identify multiple processes listening on the switchboard. So this is all like a bit lame, doesn't really look exciting. So here's a more sort of practical example of how you could be using it in practice. So again, you start the switchboard, but instead of using flowercat, you could use CloudABI run to spawn a CloudABI process. There's a simple demo web server nowadays that's already prepackaged that you can use. And inside of the YAML, which I haven't put in this slide, you refer to the switchboard listening on TMP Flower, and you say, I want to run this process listening on Flower. Then there's another process called Flower ingress accept. And what that one does is it binds on a TCP port number, and it calls accept in a loop to accept incoming connections. But then it pushes the file descriptors into the Flower switchboard, which can then hand it over to a process on the other side. So when you run all of these three commands, you can finally run curl localhost, and you get a simple response from this web server. So far, this doesn't really look that exciting, but this is really where sort of, I'm going to describe the actual sort of value that's added to this system, is the matching that's being done on the labels. It's not like an exact matching, so it doesn't require that both sides present the same side of labels, the clients and the servers. But A valid match is constructed when there are no contradicting labels. And this allows both parties to actually attach more labels than necessary in the matching process. So clients can provide extra metadata specifying who they are. And servers can also add some extra metadata in that sense. So they can say, like, this is a web server that's running Nginx. This is a web server with version whatever. So also in this case, with the ingress, it will attach the IP address and the port number of the peer as extra labels before forwarding it over to Flower. So the process, so the process will then know like the IP address of the connecting client. So it's also capability-based, namely the handles that are pointing to the switchboard, they can be duplicated and can be constrained, and some extra labels can be attached. So what you can do is you can actually enforce that a program that makes use of the switchboard always has to identify itself. It always has to provide a label for every request saying, my pod name is www, etc. So this is sort of the resulting picture. So Scuba Runtime now has a connection to the switchboard, and for every container and pod it starts up that has a Kubernetes client or server tag, it also creates additional handles to the switchboard. So those are these lines over here. And then whenever the Nginx and MySQL want to communicate with each other, Nginx sends a request to the switchboard, which then creates a socket pair and hands out both ends to MySQL and Nginx. So that's this line over here. So the question is, does all of this actually work? Well, let's see. So let me try to do this while holding the microphone. So I hope everyone can read this. On the left, there's a FreeBSD server. I'll increase the font size a bit. Oh, okay. Well, then I'll try to hold it like this. So now I need to type in my sudo password. So what I've done now in the right terminal, I've started up a Kubernetes server, like an API server, and on the left I've started up a kubelet. So now we see that the kubelet, this is a FreeBSD VM, registered itself as being kubelet3.test.cloudabi, etc. And there on the right, you see that Kubernetes is crashing. So that's not a good sign. But yeah, it does it sometimes. But now, at least what I can do is I can run a kubectl get nodes. And you see that there's now one node in the cluster called kubelet3. So this is a FreeBSD node. I could also describe it, and then you can actually see that it's a FreeBSD node. But now what I can do is I can run kubectl create-f manifest/webserver.yaml. And nothing is happening over there. Oh, man. This is annoying. So what I'll do, I'll first finish the remainder of my slides, and then I'll come back to the demo. So the annoying thing is I'm making use of like Kubernetes master. And I've seen that the API server sometimes crashes unrelated to any of the CloudABI things. So yeah, that's a shame. View slideshow. So we'll come back to that in a minute. So wrapping up. Well, if it would have worked, there is something called Kubernetes. I think we at FreeBSD should be using it as well, if we're not just trying to catch up with Linux. We have some components in FreeBSD already, or some readily available that allow us to do that. One of them is called CloudABI, easily sandboxing. With Scuba, we can run it on the cluster, and with Flower, we can allow them to communicate over the network. So what's my wish list for 2018, or the remainder of 2017 as well? I mean, this so far has been like a solo effort. There are some number of people in IRC are also hacking on CloudABI a bit, but the entire Kubernetes thing is just me on my own. I can only work on this part-time. I also have bills to pay, of course, so that's why I also do some consulting work on the side. It would be really awesome if I could somehow do this full-time, but at the same time, I'm also really hoping for participation from the community. So it would be awesome if other people could use and test this, hack and port stuff, also help me document this and promote this at other conferences, etc. And also eventually fund and invest so this can become something sustainable. So most of this work, this only works on FreeBSD, but in theory, this could also be done for the other BSD. So even if you're not a FreeBSD fan, then, and you're still interested in CloudABI, please get in touch. I mean, we can also always get this to work on other BSDs. So here's a bunch of links to GitHub repositories. So the patched up Kubernetes source, the CloudABI definitions, Scuba, Flower. A lot of these things are already in FreeBSD ports, and if they're not, a main reason for them is because they are CloudABI binaries, and those are packaged in a separate repository that you can just add to package through a config file. So this is actually all my slides. I'm now going to look at Olivier. Is there still time for the demo, or shall we? Shall we do the demo? Okay. So what I now need to do is actually not all that hard. I just need to shut down all of Kubernetes and throw away all of its state. So I'm just going to do that now with 2 hands because I need to type. No. No, this is just a testing cluster consisting of 2 nodes. Yeah. So the question is, does the API server also always crash in production? And the answer to that is no. The reason why this one crashes is that this is just like Git master that I checked out at some point in time and had to patch up to make work on FreeBSD. So there's a small number of changes to actually make it, like to add the FreeBSD bits to make it work, and also some CloudABI changes. That said, this version of the API server always crashes, like with a 30–20% chance. So yeah, I just picked an unlucky revision, but the eventual version shouldn't crash all day long. So now I've restarted Kubernetes again on the master. So the right terminal is a Linux system running the Kubernetes master. And the left one is the FreeBSD system running the kubelet. And now you can see that it has successfully registered again. And now we don't see this ugly backtrace in this terminal, which is good. So now on the Linux server, I can run kubectl get nodes. And indeed, we see that kubelet 3 has registered itself in the cluster. kubectl create -f. We now see some output here in the terminal. That's because it has now started a couple of jobs. If I run kubectl get pods, you can see that it now has spawned 3 web server processes on this node in the cluster. If I would describe them, I would get more info. You could actually see on which node in the cluster it's running, when it was started, how much resources it is using, etc. One thing I could, for example, show you is how to sort of increase the number of jobs. So if I run kubectl edit, deployment web server, I just get spawned in Vim, and I could head over to this line indicating the number of replicas running on the cluster. If I would just say, like, let's change this to 5 and exit Vim, then voila, you see in the left terminal that it generated some more output in the meantime, but now we have 5 nodes running on the cluster. So one thing that I could now do is, like for the sake of this demo, expose one over the network, and you can actually see what this web service that I spawned on the cluster. So I'm now going to run sudo flower. I'll just type it in first and then explain to you what it does. So this command over here where I say, I'm now going to start an ingress that's going to listen on port 80 and send all traffic over to one specific pod in the cluster, namely server, Kubernetes pod name is web server, etc. If I'm now going to start this, then this web server will be listening on port 80. Which has now worked. It has spawned my web server that's like serving some kind of silly HTML page on the to the browser that I found on the internet. It's quite impressive. There's 1 kilobyte of JavaScript, and it's printing itself. So right now, you see that like the networking part through Flower is sort of working. The only thing that's sort of missing right now is load balancing support. This is still something that needs to be added to Flower. So you could see when I started the ingress that I directed all traffic to one specific instance of the pod. This, of course, needs to be extended that you can provide the name of a service to redirect all traffic for a service to all of its backends. So this is still on the to-do. So this is just a really tiny demo to show you that, like, in fact, this does work. This does spawn jobs in a cluster. And these are all sandboxed. All of these web servers over here, please hack them. There might be security bugs in them. The fortunate thing about it is these jobs are all started up in such a way that they can only communicate with the Kubernetes log and the switchboard. So the impact of that would be fairly minimal. Are there any questions?
Yeah, thanks for the talk. You said that the Python was ported to support CloudABI, right? Yeah. Does the Python program need to support it as well?
So that's a really good question. So we have a version of Python that works on CloudABI. There is a Python executable, but it doesn't have like the same startup process as the traditional Python one. So it's not just Python space file name. What you do is you write a YAML file in which you specify which include paths that Python is allowed to use, and you specify the file name of the Python script that needs to be run, and maybe some other resources on which your Python script depends. And then you can use CloudABI-run on the Python interpreter, specify, giving it the config file that lists all the resources that it's allowed to use. Does that answer your question?
What about the network sockets and file descriptors, open files and stuff like that?
So you're not allowed to call just plain open inside of Python, but all of the resources like directories on which you depend and network sockets, they can be passed as arguments onto the Python script. And what happens is that inside of Python, there's no sys.argv anymore. There's no sys.environ. But there is a sys.argdata that gives you access to all of the attributes that you pass in the YAML file. But I can always use a new maintainer or more people who want to hack on our Python port. I mean, at one point I was looking into porting Django. That sort of stalled halfway along because I got distracted by all of this Kubernetes work, but could always use more people looking into it. Thanks.
Hi, I have two questions, if you permit me. First, while you have to pass file descriptors in advance, you can pass a descriptor to a directory in CloudABI, and then you can use OpenAd beneath that directory to subsequently open arbitrary files. So we can run interpreted languages like PHP, FPM, and stuff, opening arbitrary scripts.
Yeah, so if you would want to have a web server that spawns up a separate PHP process to run a script, then you would also need to pass in a file descriptor of the executable of the PHP interpreter. But passing in directories means that you can also access any files within and generate new file descriptors based on those things. So it's not as if you're limited to the file descriptors that are being passed in a startup. It's only that those limit to what you can actually infer. So any directory underneath a certain directory can have its own separate directory descriptor that you can open later on.
Great, and why would you want to put the load balancing into Flower instead of CloudABI-fying something like AJ proxy?
Well, that's a really good question. Maybe we should. Now, so one of the things that I also, so this is sort of slightly unrelated to, well, it is somewhat related to load balancing. I also want to add support for DNS lookups, not added inside of Flower, but added as a separate process. So one of the things that I didn't show in my slides is that there's also, in addition to an ingress, there's an egress that allows you to make outgoing connections. So CloudABI processes could connect to jobs on the internet. For that, we also need to have DNS support, of course, because only connecting by IP address is just plain ugly, doesn't make any sense. And that is also load balancing in a certain way. You're resolving a certain host name, google.com, it may return multiple IP addresses, and then Flower needs to sort of take a look at all of those results and pick the first one or use some kind of logic to make a successful connection. So I think that load balancing and DNS support are sort of somewhat strongly related to each other, and therefore we might see that this is being solved in Flower. But this is still on the drawing board. If you want to help out, have a nice chat about it, give your input, then just counts for everyone. just ping me.
Any other question?
Could you go back to the SED slide for a moment? I want to take a picture.
Sorry, which slide? Sorry, this said? Oh, this one. Yeah, oh, yeah, the regex. Yeah, I get it, sorry. Yeah. There's another question back there.
Are you going to upload the slides somewhere? Just so I can show you to Linux people what crazy things you're doing and what might be actually interesting.
Yeah, so my plan is whenever conferences have some kind of facility for uploading slides, I will. So I'll probably send it over to the program committee. Yes?
Yeah, just send it.
Yeah, and then it will appear on the website. Yeah. Any other questions? Why do bananas have a curve? There's a...
You mentioned the lack of traceability of applications in the traditional Kubernetes setup. And is there any support for tracing, like a simplified TCP dump or some similar command for doing this with Flower?
There might be some third-party automation around it. Kubernetes doesn't really provide something like that officially. And I think one of the main reasons is because they, instead of focusing on looking at TCP packets, they are looking at the bigger picture in a certain way, and they're more interested in tracing requests, tracing RPCs over a larger cluster. You know, RPC gets sent from A to B, gets forward from B to C, and there is a sort of an open source tracing framework that's also part of the Cloud Native Computing Foundation, but it is in no way focused on TCP dumping. Yeah.
So right now, what kind of strategy you have for the load balancing part? Because now you get control over that, you can maybe implement whatever you want.
Do you know any good strategies? If so, yeah, help me out.
I mean, you can maybe implement it for implementation, and based on the experience that we get, try something else and have it as a playground for different kind of things.
So one thing I did think about is that all of the load balancing, or at least announcing which targets to which you can connect, can be placed in a separate process that hands that info to switchboard. And in addition to just giving the names of the things to which you can connect, we could also add like weight scores. So if you would want to make sort of a more complex load balancing thing, you could have some dynamic weight computation in it, so that if one backend discovers that it's sort of being overloaded, then it will reduce its weight, causing that less traffic is being sent over. Something like that.
To a special point of presence to deal based on this geolocation. So this kind of stuff.
Yeah, so I have to confess, I haven't given it like the entire load balancer thing too much thought yet. This is all open for discussion. Yeah.
Okay, referring to the last question, did I get you correctly that Flower load balancing and Flower network switching is all about a single node? So it's local load balancing to pods and services. So
far it is.
So it wouldn't help in your global load balancing example. You still would have to imply different boxes.
On multi-cluster, let's say globalized in different data center. Like, for example, there is giants that try to implement such kind of things using the Docker API, and they do that in order to have a multi-tenant and globalize the cluster. So
yeah, so I think in general you could argue that it solves the same problem. It doesn't matter whether it's within a data center or cross data center, but I think our focus should first be on like in data center load balancing, because it's unwise to smear one Kubernetes cluster over multiple data centers anyway. I mean, what happens is that like the API server will still sort of remain a single point of failure, and things slow down if you would actually try to spread it out a lot. It's often a lot wise to have like in every data center one Kubernetes cluster. And therefore, I think that Flower should for now mainly we should look into adding in data center load balancing and across data center load balancing. That also involves BGP and maybe all sorts of other like network logistical problems that are sort of out of scope for Flower. Yeah. Did that answer your question? Okay.
Okay. Thank you, Ed. And now it's time for lunch.